Welcome back. So in the national competition, the winning rocket is the rocket that gets as close as possible to 100 meter maximum height. So your rocket has an initial speed of 50 meters per second, and you can adjust its angle anywhere from 20 to 90 degrees. So what angle will your rocket reach a maximum height? So not 100 meters, but at what angle will it go the highest? So let's have a think. So you can adjust it from 20 to 90 degrees. So if it was at, let's say, 20 degrees, its trajectory might look like that. If it was at 90 degrees, we have a clear winner, right? If you shoot it directly upwards at the same speed, it will gain the most height. However, it gains no horizontal distance as a consequence of that. Cool, so that's part A. Part B, you're testing it out and your first launch is done at 45 degrees anti-clockwise from the horizontal. So sketch a vector diagram to show the initial velocity and calculate horizontal and vertical components. So, B part I. It is 45 degrees, so here's our horizontal, aka the ground, and it is anti-clockwise and at 45 degrees, something like so. So we can label that as 45 degrees. So up and to the right, northeast. Now this is our resultant vector, so it is the initial velocity, and we were told that that would be 50 meters per second. Alright, its initial speed 50 meters per second. Now a vector can be split up into two vectors going horizontal in the horizontal and the vertical direction. And why we do this is to simplify the problem, because it's much easier to work in one direction, like vertical and then horizontal, than to work in two dimensions at the same time. Right, it's possible, but in level 2 physics, that's what we're doing. We're splitting it up. So vertically, it has a component that's going up, right? It also has a component that's going to the right, like so. And we can work out the value, the magnitude of those vectors, of those velocity components. So I will label the vertical component Vi for initial, but then y because it's in the y direction. And then I'll label the horizontal Vi because it is initial velocity, but with an x, because it is in the x direction. So working out vertical velocity, VIY, is equal to the resultant, 50, times sine of the angle. Now where does this come from? So back to right angle triangles trigonometry. We have the angle, we're looking for the opposite, and we know the hypotenuse. So sine of the angle is equal to opposite over hypotenuse, where opposite is VIY. So rearranging by timesing by 50, we get VIY equals 50 sine 45. And by that same logic, VIX is 50 cosine of 45. And if you work that out, so menu, run math, 50 sine 45. Now, you might think, alright, we're done. Please hold. In an exam, your calculator is reset So you need to check by hitting Shift menu that you are in degrees. I was not in degrees, so that answer that looked reasonable is actually complete rubbish. So make sure to set your calculator to degrees before you do any calculations using your trig ratios and degrees. So we can now go back to run math. So exit. Let's try that again. 50 sine 45. Wow. See how that is now a different answer. And sometimes, like coincidentally, radians and degrees give a very similar answer. Other times it's obvious, like giving a negative answer, but do check. So 35 point, how many sig figs do we need to 1? 35.35, or to 1 sig fig, 40. And in fact, the cos of 45 is the same as sine of 45, so we'd get the same answer. But you should check on your calculator. Alright, so we have sketched a vector diagram showing the initial velocity and its horizontal and vertical components, right, the red and the green. We then actually worked out the values of those components by using sine and cos, right, our SOHCAHTOA. And so now we can use that information to calculate its maximum height. So will the horizontal velocity, the red one, Vix, influence the height at all? No, right? It'll make it go further to the right, but it won't give any height. So in fact, we are working in the vertical direction only, and we will take the initial velocity in the vertical direction as 35.35. Notice how I'm not using the rounded version in a further calculation. I'm using the higher significant figure version. What else do we know in the vertical direction? We know acceleration due to gravity is down, so it's negative 9.8. If we're looking for the maximum height, that's a special case where that velocity is actually 0. Right, and we're looking for the distance. So we have 3 knowns, 1 unknown, which means we can solve. So let's pick our kinematics equation. Which one should we use? So Vf squared equals Vi squared plus 2AD. Substituting in our values, Vf squared equals Vi squared plus 2 times acceleration, negative 9.8, times d, which is what we're looking for. So using our calculator. Now here's a top tip. If our last answer was what we need in a further calculation, in this case it was, we can do shift minus at the bottom to give the answer. So that A and S is actually just the last number that was computed, and we wanted to square that. And notice how that compares to 35.35 squared. See how when we use the more precise number, in this case it came out to be, an integer rather than a further decimal. So 0 squared equals 1250 minus, 19.6 d. So we'll add 19.6 d to both sides. We will divide both sides by 19.6. 1250 divided by 19.6. 63.78. Or to one significant figure, 60 meters. So the rocket reached a maximum height of close to 60 meters, based off of its initial vertical velocity, acceleration due to gravity, and that we know the final velocity is 0 meters per second. Alright, question C. Now, after doing that, you realized, okay, hang on, I'm going for 100 meters, right, exactly, but you only got 63. So you need to now work out the angle to get exactly 100 meters. So you need more height. So how can you get more height? Well, we'd need to increase the angle, right? If the angle was, let's say, here, the vertical velocity is greater, so the maximum height reached is greater, at the cost of horizontal distance. So we know it needs to be more than 45 degrees. Cool. So let's have a think. Oh, what is that? Alright, it's gone. So let's sketch a diagram. We know it's going to be a greater angle. We can label that as theta. We know the initial speed is 50 meters per second, and we are interested in the vertical component, right? We don't care about horizontal for now. So VIY, we know from before, VIY is equal to 50 sine theta. Now, we don't know what theta is yet, but that's fine. We could just continue on with the calculations, but instead of putting in a number, we put in 50 sine theta. Now we are looking for a distance of exactly 100. We know acceleration is negative 9.8. And for the maximum height to be 100, we also know that the final velocity, Vf, must be 0. So you see we have 3 knowns, but what are we looking for? Actually, we're looking for VIY so that we can then solve for theta. So we're looking for the initial velocity. So 3 knowns, 1 unknown. Let's pick our equation. The I, F, A, and D. It actually looks like the last one we used. Yep. So Vf squared equals Vi squared plus 2AD. Substituting in our knowns. Final is 0. Great. Vi, that's what we're looking for. Plus 2 times negative 9.8 times 100. So what's that? 0 equals Vi squared. What is that? 2 times negative 9.8 is negative 19.6 times 100. 19.6 times 100, yep. Now we add 1960 to both sides. And finally, to get Vi, we need to square root both sides. So Vi equals root 1960, which is 44.27 meters per second. Now, when you square root, you get 2 solutions, positive and negative. In this case, the negative solution doesn't make sense because that would correspond to like going down into the ground by 100 meters. Cool. So we found the initial vertical velocity, but the question asked us to find the angle. So using this expression for the vertical velocity, we can solve. So we know VI is 50 sine theta, but we know that VI is 44.27. So we can divide both sides by 50. And you'll recall from trigonometry, to find the angle, we can take the inverse sine of both sides, or the arc sine. 44.27 over 50. So on our calculator, I will go shift sine, so sine inverse. I will use brackets, and it's the 44.27, but that's actually the last answer I have, so I'll do shift minus, so to get the answer, divided by 50, close bracket. 62.3. And since my calculator's in degrees, my answer will also be in degrees. 62.3, which to one significant figure is 60 degrees. So let's recap that question. We were looking for an angle to reach a certain height. So one of the parameters we were given was d as 100. Since it's in the vertical direction, we were also given acceleration, and since it's a maximum height, we were given final velocity. So we were able to solve for the initial vertical velocity, VI, and it came out to be 44.27 meters per second. However, to get the angle, we had to use the relationship of 50 sine theta, right? And then a bit of trig to find the answer. Awesome. So next up, with that angle, what is the horizontal distance that it travels? And then finally calculate the final velocity as it hits the ground. So let's do C. That's part 1. Let's do part 2. So the horizontal velocity, well, let's go back up to our diagram here. We know that the angle is actually 62.3 degrees, so we can do 50 cosine of that angle to get the horizontal component. So VI in the x direction is the resultant, 50, like the hypotenuse, times cos of the angle, which is what we worked out in the last question. 50. Again, in my calculator, that number, the angle, is the last answer, so I will use shift answer to be more accurate. 23.24. Or as one significant figure, 20. But again, in calculations, we'll use the more precise answer. Okay, so that's part 2. Part 3 was to calculate the final velocity as it hits the ground. So, it didn't say in the horizontal or vertical direction, right? Just the final velocity, which means we need to find the horizontal and vertical components and then use Pythagoras' theorem to find the resultant vector. And now, in symmetrical problems like this, the final answer is actually, in this case, will be 50, but the angle will be 45 degrees this way, or 180 minus 45, so 135 degrees from the horizontal, clockwise. So, once more, in a symmetrical problem, so from the ground to the ground, so no elevation change, the initial velocity is equal to the final velocity. However, the angle 45 degrees is no longer clockwise from the horizontal, it's actually, anti-clockwise from the horizontal, it's now clockwise. So it's at a different direction. But let's work it out the proper way. Well, I guess work it out the more confusing way, but the way that works in other scenarios as well. So once more, for this question, you could reason about it that it's symmetrical, so it's 50 meters per second at an angle of 135 degrees counterclockwise from the horizontal. But let's do it the calculation heavy but more reliable way. So we know at the end it's going to be coming in something like that. It will have both a horizontal and a vertical velocity. But this time it's the final velocity, Vf, y, and Vf, x. So if we find the magnitudes of those velocities, we can then use Pythagoras' theorem to find the final velocity. So starting with Vfx, in the horizontal direction, so we're working horizontally, we know acceleration is 0. What else do we know? We know initial is 23.24. Do we know distance? Nope. Time? Nope. Let's have a look at our kinematics equations for some inspiration. Yep, so looking at that, we have the relationship that the final velocity is equal to the initial velocity plus a times t. And if a is 0, we're left with final equals initial. In other words, v final in the x direction must be equal to its initial, which is 23.24 meters per second. Right, because it hasn't decelerated at all in that direction. Cool, so that is Vfx. Now we also need Vfy, the final velocity in the vertical direction. So let's now set up our problem in the vertical direction. Let's take up as positive. We know the initial velocity was 44.27 meters per second. We know acceleration, negative 9.8 meters per second squared down. We don't know the final velocity. That's what we're looking for. Do we know the time? No. Do we know the distance? Yes. Distance is actually 0 because it's when it hits the ground again. So its distance will be 0. So 3 knowns, 1 unknown we can solve. So Vf, Vi, A, and D. So Vf squared equals Vi squared plus 2AD. Substituting in the knowns. So we're looking for Vf, Vi squared plus 2 times negative 9.8 times 0. Would you look at that? Another goes to 0, and then when we square root, the final is equal to the initial, which is what we expected. So that's Vf in the y direction. So now looking back at our vector diagram, we have both legs of the triangle, right? Both components, horizontal and vertical. So VF is equal to the x component squared plus the y component squared, all square rooted. So that's 23.24 squared plus 44.27 squared, all square rooted. So I'll use the previous answer for my 23.24. So shift answer squared plus 44.27 squared. So that's 2500. And then we do square root of that answer to give 50 meters per second. And would you look at that? VF is, as we expected, the same magnitude as VI because it was at back to ground level. However, it asks for the velocity. So far we've only found the speed, right, the magnitude. So let's find the angle next, its direction. So a few ways to do that. Looking at our beautiful diagram here, let me just bring that down. So we could find this angle right here because we know opposite and adjacent. So let's do that first. So tan of the angle is equal to opposite over adjacent, which in this case VFX was 23.24 over VFY was 44.27. So 23.24 divided by 44.27, 0.525. To get the angle, we need to take the tan inverse of that. So shift tan, shift answer, execute, 27.7 degrees. Now that is theta, but let's keep with the convention that the original angle was measured from. So from the horizontal, counterclockwise. From the horizontal, let's put in the horizontal, counterclockwise. So this angle right here. And so what that would be is 90 degrees from that right angle plus theta. So therefore, let's just use phi is theta plus 90, 27.7 plus 90, what's that, 117.7, or as 1 sig fig, 100 degrees. And we would say counterclockwise from horizontal. Now putting our answer together, we have the magnitude 50 meters per second and the direction. So final velocity is 50 meters per second, 100 degrees counterclockwise from horizontal. Awesome. Now it is enough to have like a well-drawn diagram with the angle and the magnitude labeled, but this is putting it in a sentence as well. Sweet. So key takeaway from that is if you're looking for a final velocity, be mindful that velocity is both magnitude and direction. And if it's on a flat ground, flat surface, the magnitude will be the same, but you'll need to account for the direction. If the surface was, let's say, elevated a bit, the final velocity calculation, you'll need to go through it just like we did together for that part to get the answer, because the magnitude will be different as well as the angle will be a bit harder to work out. Alright, happy studying, see you next time.